Hi guys, this is Dr. G here, and in this video we will talk about conformations of cyclohexane. So when it comes to conformations of cyclohexane, there are three primary conformations. The first conformation, or the most stable conformation, is chair conformation, and then you have boat conformation and twist boat conformation. So as I mentioned earlier, chair conformation is the most stable conformation for cyclohexanes. Why? Because this conformation, the chair conformation, is considered to be strain-free. So chair conformation is considered to be strain-free. As you know, most of the cyclic compounds, compounds or cyclic alkanes suffer from strains like ring strain, steric strain, or torsional strain, right? So sometimes because of this strain, certain conformations could be highly unstable. But chair conformation is considered to be strain free. So that means you don't have any ring strains from angle strain, and also you don't see any steric strain, or you don't see any torsional strain for the chair conformation. All right, so in chair conformation we will learn how to draw these chair conformations in more detail in a little bit. But usually in chair conformation, the molecule kind of looks 3D in figure number A, or this is actually from your textbook. So in A, you can see how this molecule looks in 3D. So as you can see, it is like, you have two parallel carbon-carbon bonds, and then the other two carbons are going up and down the plane. Okay, so if you look through the carbon number 1, carbon number 2, and carbon number 5, carbon number 4, so carbon number 1 and 2 and 4 and 5 basically make two parallel bonds, and then 6 carbon is on top of the plane. Okay, 6 carbon is on top of the plane, and then third carbon is below the plane. Okay, so this is how you draw cyclohexanes. And boat conformation actually has some angle strain. Okay, so boat conformation actually resembles a boat. That is why we call it boat conformation. Okay, so this boat conformation actually have some eclipsing interactions. You don't have any angle strain, so no angle strain. But however, you have some eclipsing interactions. That is the problem with boat conformations. Therefore, boat conformation is slightly unstable as compared to chair conformations. But you also have a conformation called twist boat. It is actually a variation of the boat conformation, and this twist boat conformation is actually nearly free of angle strain, and also it has less eclipsing interactions as compared to boat conformations. Alright, now comes the most important part of this video, learning how to draw chair conformations. As I mentioned earlier, chair conformation is the most stable conformation out of the three conformations for cyclohexanes. Because of that, most of the naturally occurring cyclohexanes occupy the chair conformation. So it is very important that you understand how to draw this strain-free chair conformations. So the first thing that you will do is you will draw two parallel lines. Okay, so when drawing the chair conformation for cyclohexane, you first draw two parallel lines, but draw them in an angle. Okay, don't draw them straight or horizontally, just draw them in an angle. Okay, so then what you do is you connect these two parallel lines. The next step is to connecting these two parallel lines. So on the right hand side, as you can see, the parallel lines are going down. So in that side, draw a dot above those 2 points, and then connect it. Okay, draw a dot above those 2 points and then connect it. Okay, so that is the right hand side. So left hand side is going up, right? So connect those 2 points from down. Okay, from using a point that is slightly below to those two right hand side points. Okay, so once again, draw 2 parallel lines and then connect them. Okay, so this is how you draw board conformations. Okay, so you might want to practice it a little bit more. Okay, so what we do is we draw 2 parallel lines and then we connect it. And of course, this is a skeletal structure, so every end and a bend is a carbon, right? Every end and a bend is a carbon. So you have a carbon here, a carbon here, a carbon here, and a carbon here. And then of course you have a carbon here and then a carbon here. Every end and a bend is a carbon. So this is how you draw the chair conformation for cyclohexane. Okay, chair conformation for cyclohexane. Okay, so now everyone knows how to draw the chair conformation. So you should not take more than like 5 seconds to draw a nice looking chair conformation. Okay, nice looking chair conformation for cyclohexane. And then comes the most important part. Okay, so in your chair conformation, each carbon has 2 bonds, right? But of course, the other 2 bonds of carbon should be with hydrogen, right? Should be with hydrogen. So next up is locating the hydrogen positions or drawing the carbon hydrogen bonds. I mean, drawing these carbon hydrogen bonds are very important, especially if those carbon hydrogen bonds are substituted by a substituent. Okay, so therefore it is very important to learn how to draw the other 2 bonds for each of the carbons. Okay, so this is the cyclohexane ring that we have. Okay, so in this cyclohexane ring, as you could see, 3 carbons are pointing up, right? This carbon is pointing up, this carbon is pointing up, this carbon is pointing up. Am I correct? So in a cyclohexane ring, in chair conformation, you have 3 carbons pointing up. So what you do is you draw 3 vertical lines, you draw 3 vertical lines from these 3 carbons pointing up. And these 3 vertical lines are actually your hydrogen, are one of the hydrogens for these carbons. Okay, so this is a hydrogen, this is a hydrogen, and this is a hydrogen. Okay, now identify the 3 carbons that are pointing down. So these 3 carbons are basically pointing down, right? So what we do is we are going to draw 3 vertical lines. We are going to draw 3 vertical lines from those 3 carbons, and of course those 3 lines are also going to have 3 hydrogens. A hydrogen, hydrogen, hydrogen. Okay, so each carbon has a vertical line. Okay, you have 6 carbons. Each carbon has a vertical line. If the carbon is pointing up, the vertical line is going up. If the carbon is pointing down, the vertical line is going down. All right, so now comes the leftover bond, right? So we are going to draw the leftover bond. So if a carbon has a vertical bond going up, the other remaining bond must be going down. Okay, that other bond must be going down. So this carbon right here has a carbon hydrogen bond going up. So it must have another bond going down. Okay, it should be going down, and usually you can draw this line parallel to these carbon bonds. Okay, so here is your hydrogen. This carbon also has a hydrogen going up, so the other carbon hydrogen bond should be going down. Okay, I'm going to color them in blue, and this carbon also has a hydrogen going up, so the other hydrogen should be going down. Okay, and let me use the blue color so that it will be more clear. All right, so Then you have three other carbons, this carbon, this carbon, and this carbon. Their vertical bonds are going down. Okay, so if you take a look at these three carbons, their vertical bonds are going down. So the other remaining carbon hydrogen bond must be going up. Okay, so the other remaining carbon hydrogen bond should be going up. Okay, going up and going up and going up. Okay, so that is how you do it. That's hydrogen, hydrogen, hydrogen. Okay, so as you can see, red vertical lines, okay, are actually known as axial bonds. Okay, so these red vertical lines, okay, these red vertical lines, each carbon has one vertical line. Okay, so these red lines, okay, these red lines are known as axial. Okay, so if the bond is red, we call it axial. If the bond is blue in color, we call them equatorial. Okay, equatorial. Equatorial. So everyone must be able to draw their own cyclohexane chair conformations, and also every student must be able to draw axial and equatorial bonds without any difficulty. Okay, because we are going to use this concept, use this drawing in many situations. Okay, so it is very important that every student knows how to draw these axial and equatorial bonds. So let me do this really quickly. Okay, I will show you how quick we can do this. Okay, so give me a second, I'm going to show you how to draw this very quickly. Okay, first you draw two parallel lines and connect those two parallel lines, and every end and every bend is a carbon. Okay, and then you isolate the three carbons that are going up and you draw three vertical bonds going up, and identify the three carbons that are pointing down and draw three vertical bonds going down. And then those are actually your axial bonds. Those are actually your axial bonds. Okay, so these are your axial bonds. These are your axial bonds, and for now we only have hydrogens. We only have hydrogens in them. These hydrogens could easily be substituted by something else. Okay, so here are your axial hydrogens. Now let's draw the equatorial hydrogens. So each carbon now has a vertical bond going up or down. If the vertical bond is going up, the other bond must be going down. This is going down, so other one should be going up. Going up, so this should be going down. This hydrogen is going down, the equatorial bond should be going up. This axial bond is going up, so equatorial bond should be going down. This axial bond is going down, the equatorial bond should be going up. Alright, so let's color it differently. Okay, let's use blue color. Alright, so that is how you draw axial and equatorial hydrogens. Okay, so that is how you draw axial and equatorial hydrogens.